So yeah, I'm just going to be talking about the some quantum master equations. I did not have time to get into the Green's functions as a different method of doing like quantum relaxation for an open quantum system. So I guess the first natural question is, what even is a master equation? Basically, it's a set of differential equations that allows you to completely solve for everything in your system as it allows you to solve for everything in your time-dependent system. So in quantum mechanics, that usually means that you can explicitly solve for your time-dependent density matrix, because then you can describe everything. So the first one that I'll be looking at here is the Redfield master equation, where this is the actual equation itself. And then you've got this like dissipative term, where this is sort of the interaction between your system and the bath. And then essentially you're using the Redfield tensor, which looks like this. And it looks very gross and complicated, but this is actually, I think, the simplest and the easiest one to do, as far as I understand. This is the one that we usually use, like in our research group. So basically, these things are sort of like transition rates, right? So these things make up your Redfield tensor, right? So this thing describes how your system will actually relax, right? So it's called either the Redfield or the relaxation tensor. Nice things about this one is that it is a Markovian equation, right? So what that means is that you don't need to know the entire history of your system as it evolves through time. You only need to know the time immediately prior to the state that you're trying to solve for, right? You don't need to, you can go like step by step with it, which is very nice. It makes it much easier to compute things, like in a computational field like we do. And also, if the autocorrelation functions between like your states, if those decay very quickly, which they do in a lot of cases, you can reduce these to just like a single number, and they're very easy to compute. And that's usually what we do when we're doing our calculations with all the codes that we have in house here. So that makes this a very expedient way to calculate things. You just have to keep in mind that you are explicitly assuming with Redfield dynamics that the system evolves much slower than the bath, that the coupling between your system and bath are weak, and that there is no correlation between the system and the bath at the initial time. And so the next master equation is the Lindblad master equation. And so this is essentially like a framework to generate like Liouville operators. Because as far as I understand it, these can be kind of a wide range of Hamiltonian-like operators. These aren't necessarily like specific things. They're, I think the only requirement is that they have to somehow describe a transition from one state to another. So like creation and annihilation operators, if you think of that kind of a thing, that's sort of what those have to be. And this is just like, basically, if you write out these commutators, this is just another way to write it without any of that in there. And let's see, the nice, yeah, I don't know, I can't remember what all the points were that I had about this one. But essentially, this one ensures that your reduced density matrix always stays positive, just like by construction of like how he got to this stuff. It's like very like mathematically rigorous way of doing it. The kind of the issue is that as you go towards like infinite time, you will achieve the thermal state with your density matrix, but you will not preserve translational symmetry, which is a problem. But you can include additional terms to correct that. But then the issue is that you no longer achieve the thermal state as time goes to infinity. So it's sort of a trade-off of like, which would you rather have? And then there's the Nakajima-Zwanzig master equation, where the idea behind this one is to essentially use projector operators to just get down to like the part of the density matrix that you want. And these are both just different representations. This superscript I just essentially means that you're writing it in the interaction picture. And the nice thing about this one is that it's actually formally exact. Like this is an infinite order perturbation theory is how you get to this, where this guy is like a time ordering operator. The problem with this one is that usually for any sort of practical system, you can't solve this. So yeah, and that's pretty much it.
Oh, yeah.